Hello Internet, my name is Quinn and this is Blondihacks. We've got a great little side quest boss fight victory today. We're going to finish the control linkages for the cylinder drain valve system on my Pennsylvania A3 switcher locomotive. We're going to find out all the mistakes that we made in the last few weeks and hopefully fix them. So let's go. I'm actually going to start today with a little sidebar, a day in the life of a locomotive builder, if you will. This is some of the stuff that I never show on camera, but a lot of it is happening behind the scenes. In this case, I've decided I wasn't very happy with how smooth the reversing gear was operating. There was tight spots in it that I didn't like, so I dismantled it all and did a bunch of filing and loosening things up, and now that's running much better. If you've never built a major project like this, you might go into it thinking, oh, I'm going to make everything perfect before I move on. But the reality is, sometimes you get tired, sometimes you're not sure if something is good enough, sometimes you think it is good enough and then later change your mind after a couple of showers. So things just evolve over time, and sometimes you need to revisit stuff that you've done. In this case, I thought it was okay, I thought it was smooth enough, but then decided, you know what, no, I'm going to make it better now while I still have pretty easy access to everything. Sometimes you don't notice a problem until later. I was fiddling with some other stuff and noticed that my crosshead has excessive play at the back dead center position on one side. And I did some investigating, and the interesting thing here is I actually caused this problem myself. When I built this crosshead, it was actually perfect. Everything was nice. But you can see that the lower crosshead rail has excessive play in it. And that's because I was chasing a tight spot a while back that I thought was in this motion bracket area. I thought the crosshead was being forced upwards a little bit. So I filed down that little bracket area. In fact, the tight spot I was chasing was actually in the piston gland nut. So this change was a mistake. And now I've realized that, and so now I can make this little shim and stick it in there and undo the problem. And in fact, this just makes the locomotive more realistic. Fun fact, real locomotives are 80% shims and wedges by mass. That was an easy fix though. There's still a little bit of movement in there. That's necessary. These things do actually have to move, but it's not sloppy now. Quick check to make sure I haven't made anything else worse by doing that, which, you know, that happens. But everything looks good, so let's move on to finishing up the drain valve system. We've just got some control linkages left to do. First thing I need to do is pin the scotch yokes to the cross shaft. These are all parts I made previously in this series. So I have to set the distance between them, and I need to make sure that they are aligned, which I did by eye by putting a straight bar across them. And I can clamp them both in the vise thusly and cross pin them to the shaft. Some of these cross pinning setups can be pretty tricky. I eyeballed a good position for the pin with a piece of the stock that I'm going to be using to make the pins, and then drilled and reamed this out. You might notice the shaft is not completely flush with the end of that scotch yoke, and that's fine. The shaft came up a tiny hair short. I needed mine to be a little bit over nominal, but it was close enough and you're never going to see it, so it wasn't worth remaking this shaft. The pins themselves are made from precision ground 1/16 bar stock. That's this material that I'm testing with here, and those are made just by fret sawing and filing, no precision necessary there. And then on final assembly, they'll be Loctited in place. But the nice thing about using Loctite pins instead of press fit pins is that they can easily be disassembled until the last moment, which is very helpful because we're going to need to do some trial and error on assembly, possibly make some changes to things and so on. That was tricky because of how small these parts are, but that was the easiest thing, getting those two scotch yokes pinned parallel. Now I need to get the lift arm, which forms the lower bell crank, pinned onto that same shaft at a 78-degree angle to the valves in the open position. Now this doesn't have to be super accurate, so I did the inelegant method of eyeballing it with a protractor. The two main control linkages have a nominal dimension, but they're actually designed to be empirically determined after assembly. So as long as all of these linkage angles are sort of close, we'll be adjusting all of the connecting linkages to fit anyway. I struggled for a way to hold the measurement though for cross drilling. I tried scribing it on the shaft and the arm in the correct position, but I couldn't get a clear line that made any kind of sense. I need some way to remove it from the mechanism and know where this correct angle is going to be. And then I thought, well, I'm very clever. I'm going to drill and tap a set screw in the back of this lift arm. Then I can set the angle, tighten the set screw, remove it from the assembly, and cross drill it. This is the same way that the bell crank arms were done on the reversing gear, if you recall. Well, turns out I'm not 1/10 as smart as I like to think I am, because look where I put the screw. When the arm is in the correct angle, it is inaccessible via screwdriver. Yep, I sure hope I'm the looks of this operation. Well, we both know Sprocket is the looks and the brains, and she suggested tacking it in place with some super glue, which will hold it in place just long enough for me to remove it from the assembly and tighten the set screw down, and then this set screw and the glue will hold it long enough for me to get it cross-drilled. That ended up working just fine. This was tricky because the angle of the lift arm needed to be set relative to the valve spindles which are installed on the locomotive. So there wasn't really an easy way to set this without the entire assembly being in situ on the machine. Otherwise, I could have come up with some sort of fixture that would set the angle relative to, for example, the scotch yokes. But this is kind of dependent on how your valve spindles ended up getting built. This is a big moment though. With all those components cross-pinned to the shaft, I can now actually test all 4 of the valves on the machine for the first time. Let's see if they blow air when open, and look at that. The left side ones are working correctly. You can see them blowing the tissue paper away. Sorry for the compressor noise. Over here on the starboard side, also working very well. Or is it? I went back and forth testing these, and everything seemed to be working, and yet something was bugging me. Something seemed wrong, and I couldn't quite put my finger on it. Do you see it? Do you see the problem? This took me a while to notice. Do you see it? Yep. The valves on one side are open in the forward position. On the other side, they're open in the rearward position. That's bad news. As you can see, when I pull the valve spindles out, they are not oriented the same way when the hole through the spindle is vertical and thus open. Now what that means, of course, is that these valve crank assemblies are handed. And this is what's really killing me, is that I kind of figured they would be handed, right? They're left and right sides of the locomotive. And I looked really closely at the drawings when I made these to check if they were handed. I specifically checked for that, like triple checked it. And somehow I looked at these drawings and deduced that all 4 of them were the same by looking at the elevation view of the fore and aft versions of the valves. And I thought, well, they don't seem to be handed, so I guess I'll make them all the same. And yeah, I missed the fine print where it clearly states they are handed, and thus the 45-degree through hole in the spindle needs to be reversed on one side. I'm not gonna lie, discovering this error this deep into this subsystem was pretty gutting. I had a lot of hours in those valve spindles already, and the thought of redoing 2 of them was not a pleasant one. But I had a little pity party, and then I came back into the shop, put my big girl pants on, and decided the easiest fix was to drill the old spindles out of the crank arms, make new spindles, and silver solder them back into the holes. With some cleanup, that'll be a clean crank arm once again, and that way at least I was able to recover most of the work in these spindles. The crank arms and the crank pins were quite a bit of work in their own right, so I didn't have to redo those. And that recovery actually went really well. I was so good now at making these valve spindles because I've made a bunch of them, so I was pretty quick at making them, and the fit on them turned out really good, so they should seal reasonably well. And away we go. As you can see, now all 4 of them are open or closed in the same orientation. And it's neat because you can actually see the locomotive slow down or even stop when the valves are open, because of course there's a big air leak in the system when the valves are open. I'll let you listen to it here. It's pretty cool, I thought. All right, let's get on to work on the last couple of components, which are the control linkages. There's 2 of them. The first one is made from a very long piece of round bar. It's a fairly simple part to make, but the length of this actually makes it surprisingly tricky. It's always interesting how a single dimension on a part can suddenly make it quite a big challenge, depending on the machine tools that you have. The first job for this piece of round bar would be to face the ends and bring it down to final length, which should be a straightforward turning job on the lathe. I've got it fixtured here with one of my emergency adapter collets that I like to make. You've seen these before. However, you will notice that I cannot get the bar all the way in to the spindle. That's because this collet chuck is a shop-made device that was made from a Morse taper end mill holder, and thus it does not have a through hole. It doesn't have a draw tube, it has a draw bar in it. It has a decent amount of depth, 7 or 8 inches, which is almost always more than enough for me. However, this part is almost 13 inches long, so I do need to do something different. I considered drilling out my drawbar and making it into a draw tube, but the longest aircraft drill I have is still nowhere close to long enough, so that's going to be a tricky project. Another option would be the steady rest. However, every finger or jaw-based work holding system has a minimum diameter, and as you can see, the minimum diameter of my steady rest is too large for this thin bar stock, so that eliminates that option. This also eliminates all of my normal chucks. They're a little bit too large. The jaws can't close tight enough for this diameter of round bar. I could also face the ends on the mill, of course, with a collet block, but this whole situation gives me an excuse to use a setup that longtime viewers will remember that I haven't shown in a while. I have this itty-bitty chuck, and I can mount it in my 4-jaw chuck in what I like to call chuckception. This little chuck can hold a much smaller diameter stock, and in fact I used to use it a lot before I made the collet chuck, because the advantage of a collet chuck is also that it can hold small diameters. However, the chuckception setup allows me access to the spindle bore on the lathe, so I can hold small diameters that also go all the way through the spindle bore. So after dialing in the body of the 3-jaw, I can fish my stock in there, and we're in business. There is quite a bit of run out in this little 3-jaw chuck because it's a garbage chuck that I bought from a garbage site. I'm just facing in this case, so it doesn't matter. However, the nice thing about this setup is that you can dial in the inner chuck with the outer 4-jaw. So if you need it to be concentric, you can, and the quality of the inner chuck doesn't matter. However, you don't want to go too far with that because there is a lot of eccentric mass then with the little chuck, and your lathe is going to shake itself off the bench. Since I'm just facing though, I don't care about a little bit of run out, so I'll roll with it as is. Now, obviously this isn't my idea. I think I learned this from Adam Booth. People with really big lathes often hold smaller work holding systems in their big chucks, either small chucks or collet blocks or other work holding solutions that work on small things. So this is just a model engineer's version of something that the big kids do all the time. After facing both ends, I can now take a measurement, which is the excuse I've been waiting for to bring out Excalibur. Footnote, Excalibur was previously named Super Caliper, but many of my viewers think they are funnier than me, and they are correct, and have rechristened it Excalibur. Some of my viewers also think they are meaner than me. They are incorrect. The next task is to mill 2 parallel slots, one at each end, to hold the tabs where the pivot holes go on the linkage. This is tricky though because these slots need to be parallel at one end and the other. Normally you would use the collet block or other work holding for the indexing in a situation like this. However, because this part is so long, we can't do that. The stock isn't rigid enough to machine both ends without moving it in the collet block. So because of that, we cannot use the fixture itself for indexing. The part has to be somehow self-indexing so that we can move it in the collet block for each operation. How would you do that? Well, I have just the trick tool for this. It's called the rose index. This little guy can be clamped to your part before you start your operations on it, and it gives you a repeatable reference with various angle options that stays with the part as you move it around from fixture to fixture. Now I have a new problem though, and that's clearance. The end mill I need to use is extremely tiny, and I can't get clearance around the collet block without having too much stick out on the material. So, field expedient emergency collet to the rescue, one of my favorite little tricks. Drilled and reamed a hole in an aluminum block that's been squared up, big bandsaw cut through the middle of it, and presto, I've got an instant collet with lots of clearance for the spindle. One down, now I need to mill the other slot parallel to this one at the other end, and this is where the rose index comes into its own. I can pull it out of the collet block, flip it around, put it back in the collet block with minimal stick out so that I have a rigid setup, and the rose index gives me a way to repeat the position that the stock had when it was in the collet block previously. I'm just using it for square reference here, but you can see it's got 45 and 60 and 30 degree angles on it as well, so lots of options for this tool. If you want to buy one of these, and you should, hashtag not sponsored, but go ahead and buy one from Rosenthal Tools. He's the guy who actually invented it and deserves your money. There's a lot of knockoffs of this tool out there. The little tabs that go in those slots we just milled were made over here on the shaper. Very satisfying, as you can see. I rounded one edge of it as well so that that will slide into the round-ended slot created by the end mill. That piece there is both tabs, so I cut that in half, created the two tabs, and then took that over to the hearth and silver soldered those tabs in place. And the reason these tabs are oversized is so that we can position the holes as needed anywhere on that area to get the exact length of this linkage that we need, and then once everything's working, we can file down the excess to make it all look nice. There's one more linkage we need though, and that's the down link. It's got this little dog leg bend in it. It's of a particular thickness that I didn't have bar stock for, so once again, the shaper created said bar stock for me. The intent in the drawings is that you're supposed to set the length of both of these two linkages as needed to make the mechanism work. However, that's a lot of variables to try and set all at once, and I wasn't really sure how to do that, so I decided to put one hole in each of these two linkages in the nominal location, and that halves the number of variables I'm trying to come up with all at once. I put one end of that long reach rod into the end of the bell crank that's on the control lever at the cab end of the assembly. It goes in there like that. You can see how that lever now pulls that reach rod fore and aft. Then at the other end, I can set that guy into the second bell crank, which we made a couple of videos ago. It's back, and now is its time to shine. So this end will go in there, and the exact hole location in that tab is TBD once we have a position that looks like it's going to work. We weren't actually done with that down link, however. It's still straight, and it needs a dog leg in it, because as you can see, it feeds down from the bell crank to the lower bell crank where the scotch yokes are, but you can see it has to shift over to get around the cylinder head and also to line up with that lower bell crank. I scribed the bend locations on it from the drawing using the surface plate, and then I used my little press brake to do the bending. These don't have to be crazy accurate, so I just eyeballed it. Good old Mark I eyeball is actually very accurate. Unfortunately, I have the Mark II eyeball, which has an app and a subscription, and it's just terrible, so I got to spend some time straightening out my bends because they were pretty wrong. Now we should have all the parts, so it's just a case of determining the final lengths of these two linkages by means of drilling the final two holes in each of them. I wish I could say I came up with some clever or scientific way to do this, but I just ended up picking a location and marking it with the Sharpie on each linkage, and then running the valves through their range of motion and deciding if my Sharpie mark is still in a position where it would work at both extents of the mechanism, and well, that allowed me to come up with this final version of the dogleg downlink, and then I ended up drilling the hole in the reach rod in A position. Here's the first all-up test of this system. Oh, valves open, locomotive slows down, air coming out of there. Looks good. Close the valve, locomotive speeds up. That's pretty cool. It looks like it's working. Here's the driver's eye view of it. You can see that when open, there's quite a lot of air moving out of there. It slows the locomotive down a lot. Mind you, I'm running on very low pressure here. This is about 7 psi. The locomotive's been running better and better as it's running in, and it's running on quite low pressure now. In under real circumstances, you'd be running more like 60, 80, or 100 psi, so it's not going to slow down like this when the valves are open. This entire mechanism is really very cool, but it's hard to visualize all at once, so here's some split screen action of the mechanism cycling, so you can see all these little pieces that we've been making over the past few weeks all coming together. This was a very difficult system to build, honestly. This was very challenging, but it's very satisfying to see it working. There's one issue that may need addressing in the future. You can see the footboard is actually flexing quite a bit under the motion of this mechanism. We're asking a lot of a bit of brass hanging way out in space. Now, there's a lot more to build yet at the front of this locomotive, so it may be that the footboard is supported by the cradle or the smoke box or something else up here, but if not, I may come back and add a brace or a stiffener to this. Job done then, right? Everything's working? Well, not quite. I noticed after some testing that the valves actually aren't opening all the way. See that extra little bit of movement there? They're opening about 50%. And I mean, it would probably be fine. They would certainly work. I talked this over with my patrons a bit because many of them have a lot more live stream experience than me, and the general consensus was that they're probably fine. But I decided if maybe there was an easy solution to improve them, then I would go for it. There's basically two categories of options. I can modify the length of one of the linkages, either this downlink or the long reach rod, and that will have the effect of shifting the open-close range of motion on the valves, which would be a valid option because I have excess range of motion on the closed side, so I could shift that over to open a little bit. So I could modify one of those linkages to be adjustable, for example, put some threads in it, or I could modify one of the bell cranks. Changing the angle on this would increase or decrease the range of motion. Or down here at the cab end, of course, the range of motion is ultimately set by the angle of this bell crank and the length of this Happy Cyclops slot. So I could change that, but that's quite difficult to do because that was an accurate rotary table setup. I'd never get it back into that position again, and I just end up mangling the slot, so I'd have to remake the part, and making that part again is not going to be fun. After sleeping on this for a couple of days, an easier solution hit me. The range of motion is constrained not just by that curved slot, but the thing riding in that curved slot. There's a little T-pin hiding in there, and the size of the head of that T-pin is ultimately what limits travel. So I should just be able to make a T-pin with a smaller head on it and increase the travel a little bit. Let's see if it's enough. Now, of course, the new pin is a little bit sloppier in the slot vertically, but that doesn't matter. The top and bottom of that slot aren't doing anything. The motion of the lever is constrained entirely by the pivot. That slot is only providing the end stops for the motion. In fact, they could just be pins. The design doesn't need this elaborate curved slot in it. But what's great is these pins are so trivial to make that I made a bunch of sizes to experiment with different ranges of motion on those valves. As you can see from this very scientific hair blowing test, the result was a grand success. Those valves are now working really, really well. Could not be happier about this. Health and safety warning, do not perform hair blowing tests on live stream unless you hate having skin on your face. That wraps up the drain valve control system on the locomotive. I'm super happy with how it came out. Everything's working great. Thank you so much for watching. Thanks to my patrons for making all this possible, and I'll see you next time.